In the last lecture, we did a bit of a probability review, and then we ended up with looking at an example of an application which was called the hiring problem. So since probability is, it's a little important to get that under your belt, so I'm just going to do a quick review and make sure that you do recall some of the slides that we looked at last time. So we started off with the sample space. We had definitions for outcomes. So we spoke about the sample space, outcomes, and then we went on to define events as a subset of outcomes. Okay. And then we defined what are mutually exclusive events, where the intersection of A and B of two events would be 0. We defined conditional probability, and conditional probability formula was probability of A given B, intersection divided by probability of B. We defined what are independent events. Okay, so if A and B are independent, then we have the following relationship that the intersection of A and B would simply be given by the product of the two individual probabilities. Okay. We also had the chain rule for non-independent events. So that is given by the following equations. Probability, the joint probability of A, B, and C would simply be given by the following formula, which was referred to as the chain rule. Okay. And then we had the law of total probability, which came in handy when we looked at the Bayes theorem. And the Bayes theorem was given as follows. So I'm not going to go into the details of that, but this is sort of a summary of all the slides we looked at. Okay. And then we define what is a random variable. It's a function on the outcomes. Okay, so it's a function defined on the outcomes. And if you look at a couple of the examples that we said, well, the first example was we're doing an experiment where we are throwing a couple of dice, and we're defining the random variable as the sum of the two dice. Okay, so it has a probability mass function, also sometimes just loosely referred to as a probability density function. But as I said, probability density is generally for continuous variables, and here we talk about discrete random variables. Okay. So, and then we gave another example of a random variable, which was an indicator random variable. And this was defined as the indicator random variable on an event A is simply defined as having one of two possible values, 1 or 0. Okay. If the event occurs, then the value is 1. If it doesn't occur, it's 0. And we'll see more of that today. So this is something that I didn't cover, so let me just briefly cover this. What is an expectation of a random variable? So hopefully this is also something which is not too difficult. This is generally used to mean in a general way. A lot of the use it in everyday language as well to simply mean the average or the mean. And formally, it's defined as if you have a probability mass function given by the following probability x is equal to x, then you need to sum over, multiply that with the value of x, and then do sum over all possible values of x. Okay, so that's the expected value. The second moment or the nth moment could be referred to by taking x to the power of n. That comes in handy when you're doing variances and so on. Not going to be doing that immediately. So we've already defined the probability mass function. F of x can be generally referred to as the entire set of functions where the entire distribution is given. Okay. So let's take a look at a simple example of that. So if you're throwing a single dice, okay, the probability mass function, assuming that the dice is a fair die, okay. So the probability of the random value x having a value of I is simply 1/6, okay, for I is equal to 1 to 6. And so the expected value would be what? Can somebody calculate that for me? What would be the expected value for the random variable x which is defined to have values of the die itself. Somebody with a calculator. Well, let's just tell me what the equation would be. Just the numbers. So you've already said the property of X having a particular value is simply the outcome of the dice. And so to be able to calculate the expected value, you have to multiply the probability mass function multiplied by X to the power of 1, okay? And sum over all possible values of X, which are 1 through 6. So what would be the expected value, X? Just to make sure that you guys are awake. Yeah. Would it be 1? So if you're doing a summation of probability of X is equal to I without the value of X, okay, you're not doing a weighted sum. You're simply doing a summation of the probability mass function, okay? That over all possible values of X being 1 through 6, that would be equal to 1, okay? Because that's simply saying, what is the probability that some value of X comes out, okay? 2.8, can you tell me the equation? So just tell me the equation, the actual, sorry? 17 divided by 6, and the reason why you got 17 is how? Okay, so 1 plus 2 plus 3, 4, 5, 6. I think you got that sum wrong, is it right? 6, 10, 15, 21, okay? So you can also tell that the fact that, you know, again, your intuition should also tell you whether the result is right or not. I mean, it's supposed to be from 1 to 6, and it's uniformly distributed. So do you expect the number to be less than 3? So that's why your intuition should come in and should say, no, it should maybe be 3. But then you're saying 1, 2, 3, 4, 5, 6, right? And it's got to be somewhere between these two. So it's actually not going to be either 3 either. It's going to be 3.5. Okay, it's right in the middle. So it doesn't have to be equal to one of the dice values. Somebody perhaps had a response. Yeah, so we got the equation right. So that was a simple example. What if the die was actually loaded, right? So you playing around with your own die, and you set it up such that the probability that it hits a 6 is actually half, and the rest of the values are 1/10. Okay. First of all, is the probability mass function properly defined? And how would you check that? You'd simply do a sum over all the possible values of the probability mass function, okay? And that should be equal to 1. So presumably you can do that check, and you don't do the math, the arithmetic incorrectly, and you'll get a 1, right? So how do we calculate this? Can somebody tell me now? So what is your intuition? Should it be now be more than 3.5, the same, less? What's your first intuition without doing the math? Yeah. It'll be more than 3.5 because, you know, you loaded up so that the probability of 6 is higher. So what's the answer now? And if somebody can just tell me the equation. So just like Carl mentioned, we're doing the sums. Yes. Yeah. So 6 times 5 upon 10. All right. So the answer comes out to be 4.5. So this is just showing you a very simple case of doing the math and making sure that you understand what is the probability mass function and what's the expected values. Yes. Say that again. So what is it telling you? It's telling you what is the average, okay, just the mean. Just like we use it in everyday, that's how we're defining it. So the expected value is the average or mean, but when you're defining it mathematically, it's a little different, okay? It's given by the following equation, but you can imagine that Well, if you're throwing the dice, you're not really expecting 3.5 or 4.5, right? It's kind of odd because it has to be one of the 6 values. So, and that's why median is different from the mean. The median would be, say, well, what is the most likely, response? And that would be one of the responses. But when you talk about the mean or the expected value, it could actually be, something which is not one of the outcomes. Okay, but it's strictly defined as the sum. It's strictly defined by this particular this equation. But you can see that it is giving you that if you did a lot of experiments and you did an average of all of them, then it would give you that 3.5. Okay, so essentially, if you look at how if I give you this, an assignment, or I have a whole bunch of results coming up, and I say, what is the expected value? What is the mean? So it's more or less the same thing. What is the average over all the possible values? Okay, but that also depends on whether the results are skewed. So if everybody's getting very high marks, then the mean will be somewhere closer to the maximum. Okay. So that's the expectation of a random variable. So some other properties of random variables. Now, we spoke about what happens when random variables are independent. Okay. One of the things that should come out is that the joint probability, okay, is simply the product of the individual probabilities. And that comes in directly from one of the early equations where we said that, if you have independent events, and they're often called mutually independent events, which means that if A and B are mutually independent, then that means that, they're only independent from each other. But there could be other random variables which are correlated. Is that a question? So when you have, you often come up with this term mutually independent random variables. And so you'll see that often is that if you have mutually independent random variables, which means that x1 through xn are now not dependent on each other, then you have some of these properties which are nice to have. Okay, that the expected value, again, the expected value can be calculated from the following equation. Okay, so you keep on using this equation, and you can, if you spend a few minutes, you can prove this. Okay, I'm not going to do it over here because it'll take a bit some time, but you can prove all of these directly from that equation. All right, and you would have to use a fact, this particular fact, and you would have to do maybe a double or triple summation or something like that. Okay, but it can be done. So these things are nice to, there's also sort of intuitively obvious. All right, but if you really want to go back and prove this, you should be able to do that with a little bit of mathematical manipulation. So let's get back to where we stopped in the last lecture, which was the hiring problem. Okay, so I'm just going to restate it. We had a fair amount of discussion on that. So you are using an employment agency to hire an assistant. The agency has N candidates and sends you one candidate each day. You interview the candidate and must immediately decide whether or not to hire that person. But if you hire, you must also fire the current person that you have, that you recently hired. Okay. The cost to hire is simply given by C per candidate. Okay. There's also a cost of interviewing, but I'm going to neglect that. And so if N, you're going to be interviewing all N candidates, okay? And of those, X are going to be hired. Let's assume that X is some random variable. Then the cost of hiring is simply going to be C times EX. Where'd that come from? Because X is a random variable, and we're saying that we want to, and this is an example of what expectation means. Okay, so you have a whole bunch of, you're getting a whole bunch of candidates, and what you're saying is that, well, it's possible that if you got the best candidate right at the beginning, then the cost would simply be C. You're just hiring one person. But if the agency manipulated the data and somehow they sent you the worst candidate and then the second worst and so on, and finally they sent you the best candidate, you'd actually end up hiring all of them. And in that case, the worst case would be C times N. Okay. So, but assuming that the input is coming in some kind of a distribution, okay, and then you might guess what that distribution is, but you don't have experience with that agency, you don't know what the distribution is going to be, okay. So that's the tricky part. is that how do you actually estimate what your expected cost is going to be? What do you expect from after hiring a whole bunch of candidates? So let's convert this into simple pseudocode. All right. So the code is as follows: hire assistant given n. Okay. So this is, you have n candidates, and now you're supposed to decide on how to hire them. So you define best to be a sort of a sentinel. Initially, a sentinel candidate is candidate 0. So best is essentially the best candidate so far. Okay, and you start off by saying from you're going to set I to going from 1 to n. You interview each one of those candidates. You interview the first candidates, and the first candidate naturally has to be hired because you don't have anybody else. Okay, and then you hire the next candidate, and if that person is better than the previous candidate, then you're going to hire that person. Okay, so if candidate I is better than the candidate best, that's the best so far, then you're going to replace best with I, and you're going to hire that particular candidate. Okay, so hopefully the pseudocode is clear to everyone, right? Question here. Okay, so let's go forward. And if somebody can tell me how to get rid of this, it didn't used to happen until a few weeks ago. It just started coming back again. Anyway, so let's go forward. Now, the next thing what we'll do to be able to analyze this is we're going to simply associate a rank. Okay, and we're going to say, well, let's say the candidate, we presented 3 candidates, 1, 2, and 3. And we're simply going to say the rank is sort of how good that candidate is. Okay, so let's assume that the candidates presented in the worst first, okay, and then we got the best, and then we got the middle one, right? So in this case, what's going to happen? Are we going to do the hiring? How many people are we going to hire? 2, yeah. So clearly, we're going to hire the first person, even though he's the worst, because we don't have any other person yet. And then this guy is better than this guy, so we're going to hire him or her. And then we presented with somebody who has a lower rank, so we're not going to hire them simply because we've already found the best. Okay, so we're comparing it with the previous, with the current person who's been hired. So this tells you that in this particular example, X comes out to be 2. We hired 2 people, right? So now the question is, and we're going to make it a little bit more complex. Wish there was some way to place it somewhere that it doesn't show up. Okay, so now we're going to use what we defined earlier, which is indicator random variables. Now to be able to solve this problem, we're going to define indicator random variables xi. Okay, so xi is going to be, remember what the indicator random variable was, just going back one more time. Okay, just making sure that remember this. So an indicator random variable defined on event A is equal to 1 if that event occurs. It's equal to 0 if that event doesn't occur. Okay, it's just telling you if that event occurred or not. Okay, it just has 2 values. It's a random variable which has 2 values. So now we're right here, and we're saying that we're defining these indicator random variables x1 through xn, which are essentially defined as the following: x of I is equal to the indicator random variable if the ith candidate is higher. Okay, so let's take a look at what x of I would be. So in the first case, because we're going to be hiring this guy, okay, so the x1 is going to be equal to 1, right? Because we're always going to hire the first person. The second person happens to be the best. So we're again going to hire that person, and the indicator random variable is going to be 1. And then the third person is not the best. And since we've already found the best candidate, so the third person is not going to be hired. And so the indicator variable x3 is going to be 0. Okay. So again, this is the example where the sum of the indicator random variables X is going to be the sum of these three, all of these, and so it's going to be 2. And that's going to represent a particular instance of this particular hiring process. But in another instance, it's quite possible that you will get a different order. Okay. So so let's take a look at this particular slide. And now what we're saying is that here we have 3 cases hired. Okay. And we're saying, well, I think I'll go to another slide. All right, so let's take a look at this particular slide. So let's assume that we have the probabilities are uniformly distributed. Okay, so you have 2 possible. So far we've only got 2 candidates. We hired the first one, and then the second one's come in, and now we've hired 2 people. So if I ask you the following question, what is the probability that candidate 2 is the best so far? Okay. Assuming that they're uniformly distributed, question is, you had the first candidate, now you have the second candidate, and what I'm asking is, what is the probability that the second candidate is going to be hired? Yes. 1/2, okay. Would anybody agree or disagree with that? So now we're saying it's uniformly distributed, right? So can I get your name once again? So Logan, right? So Logan is suggesting that just because it's uniformly distributed, that's a thought, I presume that's a thought process. The probability sort of seems intuitive that, it's going to be 1/2, right? The fact that you had an earlier candidate, now this candidate could be either worse or better. So it seems natural to say, well, it's going to be 1/2, okay? And that seems to be right. So so how did we actually do it? The way we did it is that we said there are total possible 2 permutations. Okay, one permutation is the following, that the ranks could be 1, 2. In other words, first was lower and the second was better. Okay, or it could be the other way around. It could be 2, 1. In other words, the first candidate had a high rank and the second candidate had a low rank. And what we're essentially saying is that there are a total of, if you have 2 people, there are 2 factorial permutations. Okay, and by saying that it's uniformly distributed, we're saying that each one of those permutations are equally probable. Okay, so this has a probability of half. This has a probability of half occurring. Okay, so it's equally probable that the second candidate was better or the second candidate was worse. Okay, so if the second candidate was worse, you'd only hire 1 person. If the second candidate was better, you'd end up hiring 2 people. Okay, so now let's continue with this thought, and your answer is correct. So let's continue with this thought. What if there are 3 people? Yes. Sorry? 1 by 3 factorial. So the probability that the candidate 3 is best is going to be 1/3 factorial. Yuvraj, right? So Yuvraj is suggesting it's going to be 1/3 factorial, which is 1/6. Anybody else? Any other thoughts? What's the probability that the third guy is the best? It's a good guess. All right, but I need more suggestions. So what you're saying is that maybe you've got an equation and you're saying it's going to be 1/i factorial. Is that sort of like the general equation you're heading towards, that the probability that the ith guy is actually the best is going to be 1/i factorial? How many people agree or disagree? Yes. And can I get your name? Thomas? Okay. So you've got Yuvraj and we've got Thomas, right? And we've got 2 possibilities. So you guys have to work now. So this is 1 track. Well, in this case, it comes out to be 1/6. And Thomas is saying 1/3. Anybody would like to give it further thought before we do the voting? Yes. Just can't presume the probability. Okay, so you have a thought, but let me argue the other way around. So if you're already choosing, at every stage, you're choosing somebody who's better than the previous case, so it sort of implies that the last candidate, if he's hired, he or she is hired, will naturally be better than all the others. You get that, right? Because of the way we're doing the hiring process. Okay, so would you like to volunteer a response? Which one do you think is going to be? You're not sure? Okay, the gentleman in the back, yeah. 1/3. Okay. Ika? Okay, so you suggesting you, Raj. Yeah. Okay, got it. So yeah, so a lot of people seem to be agreeing with Thomas. Yes. No. No, all we're saying is that you have 3 candidates. What is the probability that the third candidate is the best so far? Okay. Now I've got a hint over here, right? If you look at this and just think about what I've already said in my earlier slide. Okay. So I said over here that there are n factorial permutations. That's perhaps where Yuvraj is getting his idea from. The n factorial permutations, and all of them are equally likely. Okay. Now I've given you a hint over here. What are the n factorial permutations? So there are, in this case, there are A through F possible permutations, right? You could have 1, 2, 3. You could have 1, 3, 2. You could have 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Okay. So there are 6 possible permutations. And by saying that they're equally probable, we're saying that each one of those permutations is equally probable. Okay, so each one of them is 1/6 in probability. All right, so each one of these cases is 1/6. And now what we're saying is that in this particular scenario, what is the probability that candidate 3 is the best so far? Yes, 2/6, right? So I think now we're sort of converging. And if you just look at this, how can you just use this to be able to confirm what Thomas is saying is correct? Yeah. Yeah. So I'm not sure if I got you, but you're basically saying there are 2 possible equally probable scenarios where candidate number 3 is the best. Okay, and those are 1, 2, 3, or it could be 2, 1, 3. Okay, so both of those in both of those scenarios, candidate 3 would actually be the best so far. Okay, and so by now you should be able to see that it's not going to be 1/n factorial, but it's actually going to be what? What's the equation for that? Yes. Okay, you're really into factorial. So you're saying I minus 1 factorial. Okay, very good. Divided by I factorial, which is what? 1/I. Yeah. So yeah, you got it right. Okay. So essentially that's what we're looking at. So in this case, as you can see, there are 2 scenarios. and it's going to be 1 upon 3. And when you have 4, what's the probability that the fourth one is now the best? Is going to be 1 upon 4. Okay, so you get that logic. Okay. So now you can see that the probability that the candidate I is the best so far is given by 1 upon I. All right, but this is making an assumption that the probability distribution is uniform. All right. However, we know that that is not necessarily the case. Okay, because what we could have is that the agency is manipulating the situation and maybe giving you, maybe they're not completely manipulating it, so they don't want to be caught, but they might be using a distribution which is sort of maybe a little bit more like this. Okay, so towards the end, they're sending you out the best candidates, and you don't really figure it out until you've hired them for a whole bunch of times, and then eventually you just decide to get rid of them and hire another agency. Okay, which maybe is more uniform, or maybe is sending you the best candidates first, but whatever. So the challenge here is that how do we come up with an expected number, which is something that we can sort of sleep on, okay? So that we know that the expected number is not going to vary too much, depending on the agency. Every time you hire a new agency, you don't know what their distribution is going to be, right? So what do we do? And this is what we sort of ended with the thought in the last lecture. So what should we do if we didn't really want to rely on the distribution of the agency, its own peculiarities? Yes. Yeah. So that's the whole thing about randomization, randomized algorithm. I mean, it's kind of trivial to put it that way, but it has a whole class of algorithms, and all that you're doing is you're simply taking the data and you're randomizing it uniformly at the beginning. And then you're applying the same algorithm that you would otherwise apply. All you're doing is just one additional step, okay? So this is what we're going to do. So this is essentially the problem that we had. We can assume that the candidates are coming in some kind of an order, maybe random. However, we don't really know the probability mass function, the distribution of the candidates. Okay, and so the randomized algorithm basically says, well, all we'll do is we'll take the original algorithm, all right, and we make some changes. So now the agency has to send us the entire list of n candidates in advance. And then we're going to randomly, so we're going to have our own random number generator, and we're going to somehow be able to use a random number generator, which makes sure that the candidates are now uniformly distributed. Okay, so the same algorithm, which was as before, all we've done is, so in every randomized algorithm, this is all we're going to do. Okay, we're going to somehow randomly permutate all the inputs. So if you have a whole bunch of numbers that you need to sort, okay, a randomized algorithm of, let's say, merge sort would simply take the data. It would initially go through a randomization and then apply merge sort. Okay, so you can take any algorithm and you can convert that into a randomized algorithm. Okay, so now let's try to figure out what the answer would be. So as you can see that we've already said that the expected value of the probability that the best candidate is I so far is 1 upon I. Okay, so now we need to calculate the expected value of EXI of EX. Okay, so the way we're going to do that is we're going to say, well, the expected value of EX, and X is simply the summation of each one of these. All right, so we do a little bit of math, and we essentially what we're doing is we're taking this summation. Okay, so we're doing 1 plus half plus 1 upon 3. This is what it's going to be if there were 3 candidates. Okay, if there were 4 candidates, you would simply do 1 plus 1. Okay, so does anybody know the equation for this? And what is this particular series called? So it's a little tricky. Might have come across this series before. 1/2, 1/3, 1/4, and so on. And now the question is, what is the sum of that series? Yes. Sorry? So that's a good. So is that log of n? Can I get your name? Jonah? Okay, so that's great. And where did you get that from? Sorry? Oh, Cal2? Okay, great. So I'm glad they're teaching you something useful in those Cal courses. Okay. Yes, so that is correct. Okay, and there's a name for this series, and it's called a harmonic series. Okay, so I'm running into battery problems. If I turn this off, can people still hear me? Yeah. Okay, good. So I'm going to talk a little louder so people can hear, but this is called a harmonic series, okay? And the sum of the harmonic series is, for those of you who've taken Cal2 or otherwise just refer to the appendix, is actually order of log n. So it's actually, it's not exactly log n, but it's log n plus some big O of 1. Okay, so there's some constant as well. So we can simply say that the expected hiring cost is going to be big O of log n. Okay, and the base doesn't really matter because we're simply trying to get an order of magnitude complexity. So an example of a maybe a realistic problem, and we've been able to solve it using probability. Okay, and we used we used a special technique, as you might say, that we use the following indicator and random variables. So this technique is quite useful. It comes in handy a lot of times. Okay, so if you can't really figure out how to actually solve the problem, you could refer to this particular technique, which says, can we use indicator random variables to be able to solve this? Okay, and you'll see this perhaps a lot more as you go forward in examples and worked out examples. Okay, so that brings us to the end of the first part of our course. Okay, and now we're going to start what is the part 2 of CLRS. And so far we've sort of done the introduction. We've introduced a lot of things which will come in handy. And now we're going to look at a lot of different scenarios. And we start with looking at a class of algorithms which are referred to as sorting algorithms, which I'm sure you've come across before. Okay, and we'll start off with an algorithm which is referred to as Quicksort. How many of you have seen this before? Well, everybody who took Comp2 with me has seen this before. Okay, some people haven't seen this before. Okay, so this should be a revision for a lot of you, but we're going to do it a little bit more in depth. So let's take a look at how Quicksort works. So it's an example of a divide and conquer algorithm. Okay, and we'll assume that we have an array which comprises of, let's say, starting from element P to element R. So P could be 1 and R could be 10, for example. And so let's say it has n elements in it. And we want to be able to apply a divide and conquer paradigm. And it's sort of similar to merge sorts, which we've already seen, but completely opposite. Okay, just revert everything that you saw in merge sort. Okay, in merge sort, what we were doing was we were, doing all the complexity was different. Okay, so let's take a look at how this works. So we're going to start off by assuming that one of these elements is going to be used as a pivot. Okay, so as the book does it, the last element is assumed to be the pivot. So AR, which is the rth element, is used as a pivot. Okay, and then we divide up the array into into three parts. Okay, so the first part is we come up with a value q. Okay, and everything before from p to q minus 1, all of those values are going to be less than the pivot. Okay, and that's how we do that. Is going to be we're going to take a look at how that is done shortly. And everything in this part of the array is now going to be greater than the pivot. Okay, so fairly straightforward. We have split it up into three parts, and right in the somewhere in the middle, hopefully, is the actual pivot. Okay, so at the end of it, at the end of the initial division, this is what you expect. All right. So let's take a look at the pseudocode. It comprises of two parts. So there is the quicksort part, okay, and then there is a function called partition, which does the partitioning. So we start off with an array, as I said, from P to R. So you can assume that it is from 1 through, let's say, 10. All right. We pick, and it could have a whole bunch of values in it. We're going to pick the last value to be the pivot. All right. And we're going to partition. So the partitioning is going to be done. And once the partitioning is done, we're going to assume that everything on the left of the pivot is going to be having values which is less than the pivot value. And all the values which are going to be after the value of Q are going to be having values which are going to be larger than the pivot value. Okay. And so once that is done, essentially, we can do it, we can solve this problem in a recursive way. Okay. And then we're going to apply quicksort to each one of these sub-arrays. Okay. So now the question is, how do we actually do the actual partitioning? So the partitioning is done in the following way. We're going to assign X to be A sub R. This is the pivot. Okay. So X is going to be assigned to be the last element in the array. We're going to start off by I being P minus 1. Okay. And we're going to take a look at an example very shortly. So this to give you a quick overview, we're going to have a loop, and we're going to use values I and J to be able to parse through the loop and to be able to figure out, put things which are less than the pivot over here, and numbers which are greater than the pivot are going to be put on the right side. And then at the end, we're going to put the pivot value right in the center. Okay, and that's going to be done at the pivot value over here. All right, so let's take a look at, and at the end, we're going to return the location of the pivot value. Okay, that's going to be Q. So let's take a look at an example so that it becomes a little easier to understand. So let's say we have the following array. Okay, it comprises of 10 values going from 4, 8, 7, 2. So these are just permutations of the numbers from 0 to 9. Okay. And we start off with assigning I, so P, we're going to call this with P is equal to 1. Okay, that's the first value. And R is going to be 10, which is the last element of the array. And we're going to say I is equal to P minus 1. Okay, so P being equal to 1. So I is going to be set to be 0. All right. And then we start off by going through this for loop. So we're going to say, well, for J is equal to P to R minus 1. In other words, J is going to go from P, which is 1 initially, and we're going to go all the way up till R minus 1. Yes. Yes, I'm sorry for, yeah, so that's a notation which we haven't introduced. So that's simply going to exchange. Okay, so it's going to swap A sub I and A sub J. All right, yeah. So so what we're doing over here is we're going to now start with I is equal to 0, and J is now going to go from 1, from the first element, all the way up till the R minus 1th element. Okay, so till 9. And we're going to say, well, is the jth element of A, is that less than equal to the pivot? Okay, so in this case, 4 is less than equal to pivot? No. Okay, we're going to keep on going. We're going to increment I. Sorry, we're not going to increment I. We're just going to go to the next value of J. Okay, so J is now going to become 2, and we're going to say, is the number 8 less than equal to 3? Okay, no. We're going to continue on. We're going to go to 7, and that's also not less than equal to 3. And eventually you find a number which is less than equal to 3. And in that case, we're going to say, well, A sub J is less than equal to X. Okay, in that case, what we're going to do is increment I. Okay, so now I is going to be incremented over here. And we're going to now swap AI and AJ. Okay, so these two guys are going to get swapped. All right, so 4 is going to get swapped with 2, and this is what you're going to end up with. You're going to have 2 coming in over here, and j and 4 is going to go over here. Okay, so we're swapping those two values right over here. Okay, and then we're going to increment I. So and then we're going to go back over here and we're going to increment j. Okay, so at the start of the loop, j is now equal to 5. Okay, this is where we did the swapping, and now the j value is now incremented because now we're going for the next value of j. Okay, so at the beginning of the next loop, we're going to see I sitting over here, which is where we did the last swap, and j is going to be sitting right after where we did the swap. Okay, so can somebody tell me what's going to happen next as we go forward? So random stuff. Okay, so somebody, the audience can tell me what's going on. What's going to happen next in the next loop? To where are we going to go? What's going to be the new values before we enter the subsequent loop? What are the values of I and j going to be? Okay, given this particular array. Okay, so we've just gone through this loop. We're now going through another round of this particular loop, and we're saying now j is going to go on from, we had ended up till 4, now j is going to be 5. So we're looking at the 5th entry of the array, and we're going to compare it with the pivot. Okay, and somebody carry this thought forward. Okay, yes. Yeah. Okay, very good. And your name is? Davis. So Davis is suggesting exactly what I've shown over here, is that you simply keep going forward until you get a value of j, which is actually less than the pivot, and you're going to swap with the location of I, and then you're going to increment I, okay, at a later stage. So I is initially incremented just before we found this particular value, which is less than or equal to x, and that's when we increment I, and we're going to then do the swapping. Okay, and that's what the swapping is being done. So at the end of the entire loop, what are the values of I and j going to be? And what's the last stage of this quicksort? Can somebody tell me where is it going to end? What's the final value of I and j in this particular example? Just before we go over here, so I'm asking you, what happens when we just about to execute return I plus 1? Okay, what are the values? What is the value of I going to be, or what is actually going to be returned? Yes. So would I be equal to 5, which means that somewhere over here? Okay. So and can you tell me how you got that? Yeah. So yeah, okay, right. So you saw that I is going to be incremented up till the value of 2, okay, because that's where you're going to do the final swap, okay, because this number over here is less than or equal to 3, so I is going to come here, and 7 is going to be exchanged, and so that's where we're going to end, because now j is equal to 9, and finally we end this for loop, okay, so we're going to actually be returning the location of I plus 1. Okay, but just before that, we're going to execute this particular command as well. All right, what do you think this command is? This is doing this particular statement. So it's saying AI plus 1 is swapped with AR. Yes. Yeah. So it's going to take I is 0 over here, okay, and sorry, I is 2 over here, and so the next thing that it's going to do is basically it's going to swap, okay. So it's going to swap. 3 is going to come in the middle, all right? And 4 is going to go right till the end, okay? Because all of these values were actually, everything over here was greater than the pivot, and all values over here were less than the pivot, less than equal to, okay? And so, as you remember, what we were trying to do earlier is we were trying to put the pivot in the center, and we're trying to put all the elements which are less than equal to the pivot value to be on the left side, and all the values on the right side are going to be larger than the pivot value. And so you want to place the pivot value in the center. And so that's a neat way of doing it, is that basically you go down till the end and you say, well, let's take this particular value at location I plus 1, okay? And we're simply going to swap the pivot with that, okay? So 4 goes over here and the pivot comes over here. And so now everything, all of these values are less than 3, and all of these values are greater than 3, okay? So now essentially what we've done is we have divided the problem into 2 perhaps smaller problems, okay? And we have put the pivot in the right location, okay? So if we can somehow do the same function recursively, and we can sort this, then does the pivot actually have to be ever changed? Does its location ever have to be changed? Would you have to change the location of the number 3 depending on the result of subsequent recursive calls? No, you weren't, right? Because you know that everything to the right of 3 is not sorted, but it's all greater than 3. Everything to the left of 3 is not sorted, but it's less than 3, okay? And you might remember that perhaps, you know, you've done that, you know, sometimes when you were kids in kindergarten, you were asked to maybe sort your cells maybe in height order or something, and then you would go and stand in the middle, and you look on the right, and everybody on the right is taller than you, and everybody on the left is shorter than you, and you know that you've come to the right spot, okay? This is sort of like that. But this guy has found, he's looked on the right, and he's found everybody is bigger. Now everybody on the left side is shorter. So now this particular person knows that this is the right spot. Okay, so by making the pivot in the right spot, now we've been able to break up the problem into 2 smaller problems. And as long as we can do this recursively again and again, we have our divide and conquer algorithm. Okay. So can somebody tell me how is this different or similar to merge sort? Now think back. How did you do merge sort a few lectures ago? Right? Yes. Yeah, it's similar. And how is it different? Okay, yes. Yeah, that's a good way to put it. Conquer and divide. Yeah. Okay. So you can see that in merge sort, we're doing it completely the opposite way. Kyle? I'm not sure if I completely following you. You're saying that in merge sort, you're never going to have a worst case? Okay, yeah, well. Okay, so we'll have to wait until we do the actual analysis of the complexity for me to be able to say whether you're right or wrong. But I'm not saying you're right either. Okay, so but in order to answer your question, we have to do the actual analysis. Okay, so you just have to wait. All right. So you'll see that this is some, and if you go back to your notes, you can see that and do that analysis, and you'll see that this is completely in doing it the other way around. All right. So as the lady pointed out, doing it sort of maybe not divide and conquer, but conquer and divide in that case. Okay. So, so now that we've done that, okay, so if we go back and we say, well, we've done the partitioning, and now we're going to go back and do the quicksort. We're going to do it recursively, and now we're going to do a recursion on recursively sort this part and this part, okay? And so what we have is we've got now the new value, the new array, okay, in the following manner. This is simply coming out from here, okay? So we've got the left part over here, which is shown in green, all the values which are less than the pivot, and all the values in blue, or the ones that are not shown in blue as well, they're all bigger than X, okay? And so now we're going to apply quicksort recursively on this new array, okay? And we're going to apply quicksort on the left side and quicksort on the right side, and we're going to retain the value of X. So essentially what we've done is we've divided up the array into 3 parts. So the center is the pivot, the left side is going to be recursively called, the right side is going to be recursively called, okay? So so that in a nutshell is the overall quicksort algorithm, and we've done the division. The conquering is sorting the 2 sub-arrays by recursive calls, and the combination is fairly trivial, okay? So nothing needs to be done in combine, okay? It's really the division which is the difficult part, but the combine, and you saw in merge sort that the combined was the difficult part, okay? So because the array is actually being sorted in as we go along, so nothing needs to be done in the combined stage, okay? So now that we've understood the overall algorithm, now we look at the correctness, okay? And now the difficult part is, can we come up with a loop invariant? Okay. What could be a possible loop invariant that one could define on the partition algorithm? Because that's really the difficult part, okay? And whenever you're talking about the loop invariant, first of all, you have to identify what is a loop, okay? But there's essentially only one loop over here. So we're looking at this particular loop. And now the question is, can you define a loop invariant which is true at the beginning, which is going to be maintained, and then at the end, you're going to make sure that the loop actually terminates, and then when it terminates, it gives us something useful. Okay, remember the 3 or 4 parts of the loop invariant, okay? And hopefully stuff that I already said at the beginning of every loop can now be used to be able to define what the loop invariant is. And don't think it's that difficult. Okay, so if you can even roughly tell me what the loop invariant is, and then we can look at the exact specifics. So every time that we're starting a loop, so let's say over here, we've done one iteration. So we're about to start with a new iteration. We've got a certain value of I. We're starting off with a certain value of j. So j at the beginning of the second loop is j is equal to 5. What can we say about this loop in that could be something useful to prove its correctness? Yes. Zero and less than equal to I, or including I? So including I less than equal to I is what? Is less than the pivot value, okay, which is, let's say, is it true? So I is equal to 2, it's less than 3, 2 and 1 is less than 3, 2, 1, 0, they're all less than 3, so that looks right, okay. Anything else that you'd like to say in terms of the pivot, or in terms of the loop invariant? Is that sufficient to be able to, is that sufficiently detailed, or is there more? Do we need to say something a little bit more about the entire array? So that's a good start. Makes sense, right? But is there something more that we need to say? So you said something about this part of the array. What about for the rest of the array? Can we say something about the rest of the array? Is the rest of it? Yeah. Yes. It'll be bigger than the pivot. Okay. All right. So you're saying that everything. So the pivot, let's say, so we talk about J in terms of J. So everything J and all the way up till, let's say, R minus 1. Okay, because that's where we're ending over here, is going to be greater than X. Is that true? Is that true over here? Can I get your name? Thomas? Sorry, you have to tell me a whole bunch of times before I remember your names. So Thomas is suggesting that we're saying everything from J up till R minus 1 is greater than the pivot. And remember, the loop invariant doesn't have to be true just at the end. It has to be true at every iteration of the loop. So if you look at the iterations of the loop, is that true over here? Are all of these values greater than? Clearly not, right? So can you modify? Yes. Okay, so now you've got a modification, and can I get your name? Connor is suggesting that we modify Thomas's suggestion, and we say, well, instead of this, we're going to say everything between I to J, all right, not including I, greater than I, up till J, all right. Now that is going to be strictly greater than the pivot, all right. Is that what you're saying? Everything from I plus 1 up till and including J is going to be including J or excluding J? Yeah, so not including J. So everything from I plus 1 to less than J, that range is now going to be greater than the pivot. Okay, so that's great. And what about everything else? So everything in this range, we have said is going to be greater than the pivot. So 7, 4, and 6 are clearly greater than 3. What about this part? Can we say something about that? What can we say about that? Can we say anything about that? Can we say anything about the values from J till R minus 1, that range? Or is that the big unknown? We can't really say anything about that, right? Because you haven't even checked that. So clearly, we've divided up the array into perhaps 3 or 4 parts, all right? So one part is the one which is less than the array, less than the pivot, some portions which are greater than the pivot, some portions which are unknown, which haven't been checked, and the last part is the actual pivot itself. Okay, so we've divided up into 4 parts, okay? So here we have the loop invariant, you have A sub r as a pivot, everything up till I, including I, is less than or equal to the pivot, everything from I plus 1 until J minus 1 is greater than the pivot, and this part is not known. Okay, so you guys did a great job. So this last part generally is not included as part of the loop invariant, but the first 3 are essentially what the loop invariant could be. Okay, so what you now need to do is go back home or to your dorms and try to figure out whether you can actually prove the correctness of the loop invariant. Okay, it's not really homework, but you can try it. Okay, I'm not going to do it over here, but it should be fairly straightforward. You have to start with the initial condition and then show the maintenance as every time you're going through the loop, whether that's it's maintaining the loop invariant or not. At the end, does it give us something useful? Okay. So that covers the correctness of this algorithm. And now let's take a look at the complexity. Okay. So how would we analyze the complexity? Well, we start off with defining T of n. All right. And before that, we need to define what is n. So we start off with at the quicksort level. What is n going to be? N is the number of elements in that array. How many is that? It's going to be R minus P plus 1. All right. This is going from P to R. what is an equation for a recursive relation for T of n? So you can assume that you know what Q is. Okay, so let's say that Q is known because when you're doing the partition, the number Q comes out and the number Q depends on the pivot value, remember. Okay, because the pivot, let's say in our case was 3. So Q was placed, Q came out to be 4 because the numbers are such that the pivot's location would be in the fourth location of the array. Okay, so let's say you know what Q is. So can somebody tell me the recurrence relation? So it's clearly going to have, yes. That's good. Is that it? Is there some f of n over here? Sorry? Is there going to be some constant associated with this? Or you simply keep dividing it? So when you do the division, remember you're doing something else as well. So what you've said is exactly these two statements, right? You've divided the problem up, presumably, let's say into 2 equal halves, okay? And so you've divided the problem into 2 parts. That's where this 2 is coming in. And let's assume initially that it's been divided up into 2 equal parts, okay? That the pivot comes out to be somewhere in the middle every time, okay? This is sort of the best case, okay? So in the best case, this 2 would be there, this 2 would be there. And how much time is being taken to actually do the partitioning? So this statement over here is clearly going to take some time, right? So how much is that going to be? So what is the partitioning time? So let's take a look at the partition. Well, this is a constant, okay? Here's a for loop. And then this is some constant, this is a constant. So this is essentially the for loop. And how long is the for loop going to, what's the order of complexity of the for loop? Going from P to R minus 1. And we said that N is equal to this value. So it's basically going from R to P. So the complexity of the partition should be order of, or theta of n, yeah. So this should basically be theta of n. All right, simply because it's a for loop and it's going through all the values from P to R minus 1. Okay. So so that's good, but there is still a little bit of a problem. This is the best case. Okay, this is the best case clearly, but what about other cases? Okay. Is this always going to be true? What's the worst case? What's the worst case scenario? Best case was where pivot comes out right in the middle, smack in the middle. Say that again. Yeah. So let's say it's all the way till the end. And let's assume that all the data is already sorted, or in the worst scenario, it's always in one end. Okay, so you're always dividing up into 2 parts, and one of them happens to be a subarray, which is going to be 0. Okay, so that's going to be the worst case. So what's the worst case scenario going to be like? T of n is going to be what? Worst case. So what's the recurrence relation for the worst case? So you've got an array, you're doing the pivot, but the pivot always happens to be right at one edge. Okay, so you've broken up the problem into how many problems? Yes. T of n minus 1. Okay. And is that it? plus theta of n. Is that it? So that's basically saying, well, we're only going to do one quicksort, one recursive call, because one of the sub-arrays is actually empty. Okay, and because if that sub-array, if you go back over here, we're basically saying that this number 3 is already right at the end. Okay, so it's going to be right over here. And so the right part, there's not going to be any numbers which are bigger than that. Okay, so you're not going to call quicksort on an empty subarray, clearly. Okay, so so it's only going to be called once, and it's going to be having a slightly smaller because you've got the value of the pivot is in the right location. You're calling the quicksort again with a value of n-1. Okay. And this is this still going to be theta of n? Last question before we stop. Yes. Sorry. F of n. So f of n was just a general function, you know, and theta of n was a specific value. So think about it. Do you still have to go through the entire array? Think about it. We'll come back and discuss this next time.